Hello, my name is Anastasia Chaikova, and my goal today is to discuss how large language models can be used in multi-messenger astronomy. And I want to discuss how we use this technique with my colleague Vladimir Slotnikov in our project NIMBUS. Firstly, multi-messenger astronomy involves the coordinated observation and interpretation of signals from various messengers, such as, for example, cosmic rays and gravitational waves. The short lifespan of detected events requires rapid analysis in order to enable follow-up observation. And this field has gained significant interest in the recent years, which has resulted in substantial increase in published observation reports. Some of such observation reports services are ATels and GCN Circulars. They provide interpretation of observations. However, the highly technical and unstructured language of these reports makes them difficult to process automatically. We hope that by using machine learning to analyze and interpret these reports, researchers can more efficiently process and understand the vast amount of data that is being generated in this field of astrophysics. The successful optimization of processing ATels and GCN circulars could facilitate the rapid and accurate interpretation of this phenomena, transient astrophysical phenomena. On this slide, you can see an example of message from ATels dataset. As you can see, it mentions what has been observed, the astronomical object, in this case, the low mass X-ray binary, and also its name. Then the text proceeds to highlight the detection of a certain event, in this case, quasi-periodic oscillation, and then starts the description of physical properties, the time, the arrival, and so on. As for the named entity extraction, it is one of the ways to process textual data in order to extract structured information. It is a subfield of natural language processing that focuses on the identifying and classifying named entities, for example, people, places, organizations. In our case, the named entities can be event type, and object name, as shown on the slide. There are usually several approaches to named entity extraction, including rule-based, machine learning-based, and large language model-based methods. Firstly, rule-based methods, they use predefined rules to classify named entities, for example, dictionary lookup or string matching. But their accuracy tends to be limited by the rule set completeness, making it challenging to adapt to new entities. The second approach is a machine learning approach, and machine learning-based methods, such as, for example, hidden Markov models and conditional random fields, they usually require a large amount of labeled data. And that is almost non-existent in this field of astronomy. Also, ambiguity in words mean can affect the model's performance. And recently, the last approach, deep learning techniques such as transformer-based models have shown promise in improving named entity extraction. These models can recognize entities in context and capture complex relationship between words. They can also adapt to new entities without extensive retraining. It all sounds good for this specific domain. So let's take a little bit of closer look at these large language models. They are neural networks with more than 5 billion parameters that utilize the transformer architecture, and they are trained on massive amount of textual data. The transformer architecture relies on self-attention mechanism and position-wise feed-forward networks in order to process input sequences in parallel, instead of doing it sequentially as in RNNs and LSTMs. Transformer architecture was introduced in paper Attention is All I Need in 2017. And this architecture consists of stacked encoder and decoder layers, as shown on the right figure. In the transformer architecture, the encoder and decoder are two key components that work together for various NLP tasks, like, for example, translation or text summarization. The encoder produces a continuous representation called context vectors that carry the meaning, structure, and relevance of the input text. In the decoder, generates the output tokens by consuming these context vectors and attending to the output tokens generated so far. So far, transformers have proven to be highly effective and scalable, leading to the state-of-the-art results in various tasks, such as machine translation, text summarization, and, which is relevant for us, is named entity extraction. They can perform well on new tasks with minimal labeled data, thus demonstrating few-shot learning ability. They can also generalize well to unseen classes that were not present in the training data. And they usually do that by receiving carefully constructed instructions, which we call prompts. And it demonstrates a zero-shot learning ability. Both few-shot and zero-shot learning abilities are helpful when there is a limited amount of labeled data available for a specific task, as is often the case in natural language processing. And lastly, I wanted to talk about is probabilistic sampling. It is a technique that is used in natural language processing, where a random selection is made from a given set of elements based on their assigned probabilities. It is usually used to add diversity and to improve the creativity of generated text. And also, probabilistic sampling captures uncertainties that is usually present in language, and it serves to provide more human-like natural language generation. However, as the nature of sampling is random, we can expect that language models may not always produce accurate answers. And in order to achieve better performance, we tend to sample a model several times in order to hopefully receive a correct answer. So, as we stated before, we encounter various problems in named entity recognition in multi-messenger astronomy, such as scarce labeled datasets, ambiguity in words, meaning, and domain-specific terminology. To give you an idea of how time-consuming nature of data labeling can be, a study mentioned in the first time domain astrophysics corpus done by my colleague that presented earlier, it showed that it takes about 4.5 minutes a PhD student on average per document. And it is done already after this document was marked up by a model. It takes this time to fix mistakes if there are any or so on. This indicates the need for an effective and efficient solution. In response to these issues, we have developed an end-to-end named entity recognition system using large language models with optimized training datasets. This approach offers several benefits. Firstly, the training datasets will only contain the required entities, streamlining the training process and saving valuable time. Secondly, by leveraging the power of large language models, we hope to achieve accurate and efficient entity extraction. And lastly, we also want our solution to involve a ranking model that will assess and categorize the confidence of the extracted entities. By doing so, we hope to enhance the system precision and efficiency. So our initial focus is, of course, on gathering data and on extracting specific named entities such as event ID or object name, event type, for example, gamma ray burst, and physical phenomena or astronomical objects, for example, supernova explosion. Unfortunately, labeled datasets for these entities in multi-messenger astronomy are either unavailable or incomplete. Therefore, we manually annotated 400 messages from ATEL and GCN datasets. One of the things that complicated the process were overlapping named entities, where the same answer could apply to event type and, for example, physical phenomena. Additionally, a text does not always explicitly state the entity, and we want, for example, to infer the event type from the telescope that was used in the observation. In our research, we investigate and compare the performance of different state-of-the-art NLP models from two prominent families. The first one is GPT family, and the second one is T5 family. The GPT family includes InstructGPT, ChatGPT, and GPT-4, and T5 family includes Flan T5 with different sizes, including XL, XXL, and so on, and the model Flan UL2. The GPT family is developed by OpenAI and it utilizes the transformer architecture that was mentioned before. It focuses mainly on unsupervised pre-training through language modeling. InstructGPT is a powerful model which is fine-tuned with human feedback in order to generate responses based on given instructions. In contrast to other language models that are trained to predict the next word in a given text, InstructGPT is designed to fulfill the user's objective. T5, which is a text-to-text transformer, it is a neural network architecture that is developed by Google Research, and it also can be used for a wide range of natural language processing tasks. T5 uses a text-to-text transfer learning framework in which the model firstly is pre-trained on the unsupervised text, and then it is fine-tuned to generate text that is correct answer to a given input. And the task-specific information is usually encoded in the prompt, which is given with the input text, which allows the model to adapt to different tasks without changing its architecture. So we begin with the first approach, which is zero-shot via prompt tuning. And prompt engineering is usually a naive approach we can use to extract named entities with language models, because it is easiest to start with, easiest to experiment with. A prompt is a task description that is embedded in the input data, or a specific set of instructions that can be provided to language model during inference. The resulted prompts that we created can be divided into different categories depending on the idea behind them and the method that was used for creating them. The first type of prompt is task description. In the light of findings on zero-shot prompts potential, we decided to create task description prompts and later included examples and explanations in such prompts. We did that, included examples and explanations, because we wanted to assist the model in distinguishing between different entities and in understanding the underlying reasoning behind the classification instead of just simply memorizing the examples. However, as we saw during our experiments, if the required entity is not present in the astronomical observation, the model has shown cases of mistakenly extracting one of the entities that was mentioned in the prompt, instead of extracting it from the text. For example, it extracted a name that was given in the prompt as an example, instead of taking it from the text. We also employed the automatic prompt engineer method to generate prompts with the objective of reducing human effort and also in order to automate the prompt creation process for new types of entities in the future. In this method, we ask the model to come up with a prompt itself instead of giving it to it. And the third type of prompt is chain of thought prompts. To enhance the performance of task description prompts and to address the presence of ambiguous data that may require reasoning from a model, we decided to refine zero-shot prompts by incorporating reasoning into it. In these prompts, we ask the model to generate motivation for its answer by framing the prompt as a problem-solving task. Finally, given that event types and astronomical objects may be referred to differently in each text, we opted to minimize the number of potential outputs by establishing a predefined set of categories and then mapping entities from each text to their corresponding groups. This approach was taken in the development of the NIMBUS interface, which enables users to search ATEL and GCN telegrams within these specific categories. As another approach to the extraction of named entities using language models, we fine-tuned OpenAI Da Vinci model. We tried several approaches to fine-tuning. In the first one, the output contains the required entities as shown in the slide, event ID, event type, and physical and phenomena, all in one output. In the second one, the output contains only one entity, and in the third one, we embed the input text in top-performing prompts from the previous section with zero-shot learning. And so the output contains the entity only intended by a prompt. As shown in the table, the second approach has shown the best performance. However, it is also the most competitively expensive one, because in this case, we have to fine-tune a model for each of the entities we want to obtain. As I mentioned earlier, it cannot be guaranteed that the model will always produce accurate responses because of the probabilistic nature of sampling process. Therefore, we sample our model 5 times and then rely on the random nature of the process to generate some correct responses. Other works has also utilized a technique in which multiple outputs are generated and evaluated based on specific criteria. This approach has been employed to enhance question answering, text comprehension, and overall performance. We rank our samples based on the following approaches. The first one employs a perplexity score. It is a measure of how well the model can predict the next word in sequence. And lower perplexity score suggests more coherent and usually more grammatically accurate outputs. So we anticipate that the completion with a lower score would be accurate. Similar method was employed in different works, for example, in scaling instruction fine-tuned language models, where the model outputs were ranked also based on perplexity. Later, upon manual inspection of the generated outputs, we discovered that language models often produce accurate answers, but these accurate answers do not necessarily have the lowest perplexity. And as you can see in the table, the delta accuracy, which is the difference between the highest possible accuracy, the top 5 accuracy, where we select the correct completion when it is available, and difference between this accuracy and the accuracy that is achieved through perplexity ranking can be quite big. In some cases, it is 2/10. And in order to optimize our named entity extraction accuracy, we have developed an alternative ranking method using embeddings. This approach uses a feed-forward network. It predicts the embedding of a correct answer given the embedding of a text. Embeddings are dense vector representations that capture semantic and syntactic information about words or tokens in a continuous space. This feed-forward network comprises of 2 linear layers and 1 dropout layer. For evaluation, we compute the Euclidean distance between the answer embedding and the prediction embedding, and we choose the answer with the lowest Euclidean distance as the correct one. It is important to mention that while training a feed-forward network for ranking could be less convenient because we have to train a model for it, but its significant advantage lies in its relatively small number of parameters. The feed-forward network usually comprises of maximum 50 million parameters, and it is considerably less computationally demanding than large language models with over 175 billion parameters. So the feed-forward network requires less processing time as a result, and computer resources to produce predictions. And this makes these models advantageous in production environments where we have limited time and resources. As for why we even use these methods such as embedding ranking and perplexity ranking when we can just increase the size of a model or training data set, which can also decrease the gap between top 1 and top 10 accuracy. We do that because in the recent research, which is shown on the right figure, it shows that achieving accuracy improvement of 2/10 usually can require a substantial decrease in model size. For example, in this case, almost 8 times larger. So our embedding ranking pipeline looks like this. The large language models are represented by InstructGPT, and feature extractor networks are different GPT-based models. In the first step, we calculate the top 5 answers and their embeddings for a given text message and a prompt. In the second step, we take this given text message and predict an embedding of a correct answer for it. And in the third step, we calculate the Euclidean distance between answer embedding and predict embedding. And we assume that the answer with the lowest Euclidean distance would be correct. To understand how the model architecture and size affects the quality of output, we examine different models. Our goal is to maximize top 5 accuracy, then additionally reduce the gap between top 5 and top 1 accuracy. As shown in the table, the embedding ranking pipeline has shown better performance compared to perplexity rank in all named entities. As for the further work, we are going to use all the prediction obtained with our best performing method, in this case, embedding ranking pipeline, in order to develop Search API, whose functionality can be integrated with multi-messenger brokers and platforms, for example, with Astronomy that was mentioned before, to provide complementary information for human written messages. We are also planning to release the first version of the web application called NIMBUS for searching and cross-referencing ATels and GCN Circulars, using the data that we extracting using our approaches. As you can see on the right picture, the interface can be used for searching and cross-referencing texts. And you can do that by setting search information such as, for example, event ID, astronomical object, and other physical properties. So in conclusion, we have developed and compared approaches to creating prompts for different tasks, for named entity instruction task. To do that, we manually annotated dataset. We have annotated 400 messages from ATEL and GCN datasets. We fine-tuned several GPT-3 models and benchmarked state-of-the-art models on this task. We also developed an approach, an embedding ranking pipeline that affects more effective model sampling. And right now we are working on integration in multi-messenger alert system. Yes, that's it. Thank you for your attention.
Yeah, so thanks, Anastasia, for this dense report on LLMs, and it's nice to see this cool progress on this stuff. So, Attila, so you just clapped, or you also have a question?
Yes, I would also have a question, but it was first to clap for the work. That is really impressive.
Yeah, okay. Please go ahead then if you have a question.
Okay, so maybe I can start with a question. You mentioned that you annotated 400 documents, and I would like to know if that corpus is available. Do you plan to make it accessible for other usage? Then I can also have a look from my side and to also to see, to compare other approach on different corpus. It's also a good thing during my PhD.
Yeah, of course, we are planning to make it accessible. Right now, as far as I know, it's not published yet, but yes, it would be available.
Okay, perfect. And about the annotated, so if I understand well, you only you focused on few entity types, right? So it was the event type, the object type, and the name of the event, something like that. Yeah, object name, event type, physical phenomena. Okay, perfect. Yeah. And other questions, I don't know if I can, if we have time.
Yeah, sure.
Okay, perfect. When you said that you used ChatGPT, I imagine you use the API, right?
Yeah, the API, of course.
Okay, and a naive question, is it free or do we have to pay to use the API of ChatGPT?
You have to pay for using the API. Yeah.
Okay, I see.
Maybe, sorry, Attila, you can comment how much costs to index, I don't know, of all ATels and so on.
Well,
roughly.
It's quite affordable, I think so. Like ChatGPT model, GPT 3.5 Turbo, it's quite cheap. So indexing all the GCNs, all the ATels should be around $1,000, I think. Yeah.
Okay.
I'm not. If I remember correctly, ChatGPT is the cheapest of them all, so it might be even cheaper than 1,000 because it took me less, if I remember correctly.
Yeah,
Okay.
well, I'm talking just about orders of magnitude. So
Okay, and when we use the API of ChatGPT, are we restricted? Because now if we go on the website of ChatGPT, if there is a huge request, we cannot use. And do we have the same problems, or are we limited in a given of tokens that ChatGPT will generate?
Sometimes you can catch exceptions due to the high load, but
Okay.
you can adapt to it, make it so it doesn't stop completely. Just
Okay.
yeah,
wait a little bit.
I could add, actually there are two issues. So the first issue is just the context size of the model, which
Mm-hmm.
is, if I remember correctly, for GPT 3.5, it's 4,000 tokens, which is not enough for some of the telegrams. I could say
Yeah.
that for sure. We have to truncate some of them. And it's 8K for GPT-4, and that should be enough for everything. And some open source models that came up literally like in the last weeks, they also support 8K. So we haven't tested them yet, but it should be possible now. And the second issue, like with ChatGPT, like as a service, not as a model, is that they have 60-second timeout. So if the model doesn't generate the full answer in 60 seconds, it gets truncated.
Okay.
And if you are using API, you don't have such a limitation. So you could wait for more, but you will get the full answer.
Okay. Okay. I see. Thank you very much. And maybe last question about the results you showed on slide number 10 on the table. So the metric you used is the F1 score or the accuracy or another?
The accuracy, if the answer is the
Okay.
correct one.
Okay. Okay. So you use the accuracy if the answer is correct. Um, and how do you evaluate, for example, if because I'm not sure if it will occurs, if we mention, for example, on the text, different object names and different object type, for example, how do you evaluate if you were able to extract, to detect all of these occurrences?
Well, in the initial stages of how we did it, we did it the following way. Either the answer that we received from the model and the correct answer, they were
Okay.
identical, like
Okay.
the order of the words and stuff was identical. But then we switched to whether the correct answer contains all the entities, for example, all the names from the answer that was generated. So right
Okay.
now we are looking at this, whether the correct answer contains all the
Yep.
necessary
And
information.
yeah, and I guess this is also a difference between our both approach, our two approach, because the metrics I used, for example, I've presented you the precision recall and F1 score, is to evaluate if the language model will be able to detect all the occurrences of an object name, all its coordinates and stuff like that, instead of evaluating only one time. So I guess this is the main difference between
Yeah.
our approach. Yeah.
Mhm.
Okay. But honestly, I don't know which approach is the best. So,
Mhm. Okay.
okay. But thank you very much for your presentation and your answer.
Thank you for your questions.
Or maybe yeah, there are some questions from audience, comments.
Oh, I think that's it.
That's it. Okay, so thanks Anastasia again. So
Thank you.